Recording in progress.
Hi, welcome back. Good to have you. Nice to see your beautiful faces as always. Um, I'm going to tell you about classification today, which is basically the problem of you telling me what's the probability of some output given that I gave you some input, meaning that I want to know whether this belonged to class one or class two. So the probability of belonging to a specific class. Rather than using regression, we want to use a different approach. But in order to explain to you why regression is not a good idea to build models for classification, I want to go through a little bit of math for you to demonstrate this, why regression is not a particularly good approach. So if I gave you some data that look like this, where y was, say, two classes, one or zero. If this was your data and, an x was your vector of inputs, and you wanted to build some model that predicted whether it belonged to one class or another, you might say, well, why don't I try a linear model? Something like this. And this certainly could be done. You could use the data that I gave you and form a maximum likelihood estimate where it would look like this. And this would be a maximum likelihood estimate of the weights. Now, what's wrong with this approach? And the problem is basically that the noise in the model that we're using to find maximum likelihood makes it so that the variance of our output, the uncertainty that we have in our estimates, is going to be independent of X. But in any classification problem, that's not true. And why is that? Because so if you have two groups of data, one like this and one like this, and then you say, okay, so everything to the left, I'm going to say is class white, and everything to the right is class blue, your uncertainty regarding your classification is going to look like this, meaning that you're going to be most uncertain around the place where your decision boundary is. So the variance of what you know is going to be dependent on X. So this is X, and this would be the red is the variance of your classifier. And your classifier is most uncertain around the boundary of where it's going to fall to one class or the other. So that noise, that uncertainty is definitely not independent of X. So how do we want to handle this? So if you had a model that said y is equal to y star plus epsilon, where y star is W transpose X and epsilon, the noise, is independent of X, then the variance of y given X, which is the uncertainty that you have in the classifier, given that I gave you the input, well, that's just sigma squared, right? So that's independent of input X. But I just showed you that it seems quite unlikely that that would be the case for a classification problem. So let's go through this and show this in some formal way. So if probability of y is equal to 1 given X is, say, theta, so that's the probability of belonging to one class. So this is now just a binomial distribution describing the probability. And probability of belonging to another class, let's say, is 1 minus theta. Then the expected value of y given X, okay, so y can take on two values, 0 and 1. So that's 0 times the probability of seeing y equal to 0, that's theta, plus 1 minus theta times the probability of, well, let me write it this way. 1 times 1 minus theta. So that's just 1 minus, that's just, sorry, I screwed this up. So let me write it correctly. So the probability of y given x when y is equal to 0, its probability is 1 minus theta. And here, this is theta. So this is theta. And then for me to find the variance of y given x, what I need is the expected value of y squared given x, and subtract from it the expected value of y given x quantity squared. So what's the expected value of y squared given x? Y squared, that's 0 squared. What's the probability of y equals 0? That's 1 minus theta. And probability of 1 squared, that's theta. So this is theta as well. So then variance of y given x is theta minus theta squared. So that's theta 1 minus theta, which is equal to probability of y is equal to 1 given theta times probability of y is equal to 0 given x. So we see that the variance of y given x, my uncertainty in classifying this input x depends on x, depends on what was the x. So this probability variance of y given x is a function of x. And as I showed you, what that means is that if you have some probability like this is probability of y is equal to, let's say, 0. This is probability y is equal to 1. At your decision boundary, your variance in your estimate is going to be something that's going to be high. You're going to be most uncertain at the place where you're going to make a classification. So all of this is to say regression is not a good idea for building models of classifiers. So if you want to say either it's in this class or that class, what you really want is a probability associated with what it is that you're classifying rather than building linear models. Okay, any questions about this? All right, so the first person who formalized this idea and came up with a useful approach was Fisher. And so Fisher came up with an analysis that today we called linear discriminant analysis. And the idea is to build a linear model, but not like the way we were trying to minimize error. So remember, when we built a linear model, we said, let's minimize the difference, the square difference between what you observe and what you predicted, y minus y hat squared. That's what linear models that we built tried to minimize as our cost function. But the way Fisher thought about it is that, no, actually what you want to do is that you want to have two classes or whatever number of classes you have. You want to separate them as far as possible so that you build a model that when you project that data onto some new space, W transpose X, where you end up, your classes are as far apart as possible from each other. So he came up with a new cost function, and that cost function was the distance between the projected spaces of the means of your class, of your data, divided by the sum of their variances. He tried to come up with a way that basically did the following. He said that say you have some data X, whatever, you have this vector that you're going to classify, and when you do this classification, you're going to end up with some of them that are going to belong to class 0, and some of them that are going to belong to class 1. So let's call one of them that's going to be belong to class 0. There's going to be n0 data points that belong to this class. And they're going to have some mean and they're going to have some variance, meaning that the mean of the data is going to be mu0 and the variance of that data is going to be sigma 0. And then there's going to be another class y1 and there's going to be n1 of these data points. And that's going to have some mean and some variance. And so what does this mean here that I'm talking about? So mu0 is just 1 over n0 sum of x, where x belongs to class 0. And then mu1 is the mean of the data where x belongs to class 1. Yeah, does that make sense? So you just take all the data that belong, all the x's, all the data that belong to class 0, find its mean, all the data that belong to class 1, find its mean. I'm going to call that mu0 and mu1. And there's going to be some variance associated with each of these classes as well. So mu0 is just 1 over n0 sum of all the data that belongs to class 0 transpose. So each data point minus the mean, that's the variance of class 0, and then similarly for class 1. Okay, so far all we've done is just describe the statistics of our data. So the idea of linear discriminant analysis is that, so you're going to build a model, W transpose X. That's going to be a model. You're going to find this W that maximizes this difference between Y0 and Y1. So when you project your data, W transpose X, that's just a scalar. So you're going to end up in some space Y. This is Y. I'm going to put a Y hat on it. This is my, this is what I've found. I'm going to project my high dimensional data X into some low dimensional one scalar dimension Y hat here. And in this world, I'm going to have some data that's going to look like this. This is X0, and it's going to have a mean W transpose mu0. And then there's going to be some other class. It's going to look like this, and it's going to have W transpose mu1. So after I project my data onto this Y hat space, it's just a scalar space. I'm going to have one that's going to have a center at W transpose mu0, one at W transpose mu1. And what Fisher analysis does is it says that let's find W's so that I get this distance here as far apart as possible. So I want to get this distance here as far apart as possible, normalized by the sum of the variances of my classification projection, meaning that I'm going to have this cost here that's going to say, let's get these distances as far apart as possible. So I'm going to make J as large as possible as I find W that maximizes this distance between the means divided by the sum of the variances. Okay, so let's look at this equation for a second, see if it makes sense. So what's our problem? I'm giving you X and Y. X is a vector, Y is a class. Class 0, class 1, right? And you want to build a model that says, what does this X belong to? Does it belong to class 0 or does it belong to class 1, right? So what we're going to do is that in Fisher's approach, we're going to multiply X by W, find some W that when you multiply X by is going to give you one class. Here's the white class. And then there's the blue class that it can give you as well. And you want those to be as far apart as possible. Find W so you maximize the distance in projected space between these two classes, divided by the sum of the variance. So you want to make the variances as small as possible, the variance of the projected class as small as possible, while the distances are as far apart as possible. That's how you build a classifier. Okay, so that's the cost function. The cost function is not Y minus Y hat squared. We're not minimizing that cost function because that's linear regression. Here, we're still building a linear model, but we're maximizing the distance between the classes after we apply some weight W to our input. Okay, so find W to maximize this cost. Okay, so how are we going to do this? So look at that cost function. So that's a different kind of a cost function than we've ever seen before, right? Because it's, first of all, it's got W's both in the, so it's quadratic in W in the numerator, but it's dividing by a different quadratic in the denominator, right? So finding derivatives is not going to help us here. At least it won't give us a closed form solution. It will give us a gradient that we could iterate and find it, but it won't give us a closed form solution. But there's an elegant way to find the closed form solution to this class of cost functions. And I'm going to show you how to do that. And this is called Fisher Discriminant Analysis. So what we're going to do is find a linear model for our classifier, but one that is based on maximizing the distances between the classes so that we can basically make these classes as far apart as possible so we can dissociate the inputs. So how are we going to do it? So let's work on this equation. So what I want to do is maximize J. So let me write this J as the following. And then what I'm going to do is in the denominator, I'm going to take the W's out. Write it this way. So let's introduce some nomenclature here. Let's call this M, and let's call this S. So that's just M transpose W squared divided by W transpose SW. Now, S is a matrix that's going to be something special about it. It's a symmetric positive definite matrix because it's just a variance covariance matrices. So we can write S in this special way. We can write it as multiplication of two matrices, R transpose R, and R is called square root matrix. So it's going to exist for this particular matrix S that we're interested in. And the reason why I'm interested in writing S in this way is because I'm interested in breaking apart these two variances into something that's going to look like this. So I'm going to define a new variable V, which is going to be R times W. So S is going to be written as R transpose R. Okay, so now define this new vector V as RW. So now J as a function of V is going to be M transpose. W is R minus 1V. And then the denominator, W transpose R transpose, that's just V transpose V. Okay, so if you look at this for a second, you'll see something interesting here. So there's a vector V here, and it's being divided by V transpose V. That's like the norm of V that I'm dividing V by. So what I can do is write the following. So this quantity V transpose V is the square root of V transpose V squared, which is the norm of V squared. So then this quantity here, J, can be written as R minus Tm transpose V squared divided by which is, so this is just the numerator is a scalar, denominator is a scalar. I can write it as okay, so what I have here is a value, a number that I'm trying to maximize. Find V that I can maximize this, and I have this unit vector here, V divided by its norm. So you're trying to find a V that will maximize this equation. So look at it for a second. So you have this unit vector that's multiplying another vector. That's you're taking a vector, transposing it, and multiplying it by this vector, unit vector V. So in order to find the V that maximizes this, what you want to do is make this a scalar version of this so that it's in the same direction as that vector. So set V to be some constant times this R minus 1 transpose M. So make V to be a scalar version of this vector R minus transpose M. Does that make sense? That's how you maximize it with respect to V. So, okay, so what does that mean? That means V, so let's just set, alpha to be equal to 1. So that just means it's R minus T. M was mu0 minus mu1. That's how we defined M. Okay, so and then W was R minus 1V. We were interested in finding the weights that would maximize the distance between these classes. And so that's R minus 1, R minus transpose mu0 minus mu1. And this quantity here is S minus 1, where S was the sum of the variances. So then W is sum of the S was N0 sigma 0 plus N1 sigma 1 minus 1 times mu0 minus mu1. So we found the weights. So what this says is that if you want to find a linear classifier for your data, what you do is you take the mean of the data for one class, mean of the data for another class, and weigh it by the inverse of the variances of each of those classes. That gives you the weights that maximize the distance between the data when you project it onto the output space, Y. That's how you get the largest difference. And so our model is going to be Y is going to be W transpose X plus W0. There's going to be some bias that we want to get. And just W0 is just going to be the expected value of Y minus W transpose X, which is the residuals, basically. Okay, so that's how we build a linear model in a classification problem using Fisher discriminant analysis. So this gives us a weight for every element of our input X vector that we can use to then map it onto this Y space where we can decide whether it belongs to one class or the other. But really what we're interested in isn't necessary to build a model. Is we want to really get the probability. We want to know what's the probability that Y belongs to, say, class 0. Well, let me write it this way. What's the probability that Y is equal to 0 given that X? So that's really what I'm interested in. I want to know how confident am I that this X that I got belongs to this class. And so how do I get that? And to do that, what I need to show you is that we can find relationships between classes using ratios of probabilities. So if I'm interested in finding a ratio of probability of belonging to class 1 with respect to the probability of belonging to class 0, this this is a quantity that turns out to be fairly easy to compute. So I can find the ratio of how likely it is that it belongs to this class with respect to some other class. And this is what I want to show you how we can take advantage of this. So suppose that my data, the easiest kind of data that I have. So the first kind of data that I want to consider is one where the likelihood, the probability of X given that Y is equal to 0 and the probability of X given that Y is equal to 1, each of them is a normal with some mean and some variance. But importantly, this variance is the same in the two classes. So what does this mean? What this means is that I have some X space, and so the X that belongs to class 0, there's some distribution of X. And then I have X that belongs to class 1, I have some distribution of X as well. These two classes, suppose that the variances of them are the same. The means are different, but the variances are the same. Suppose that's true. So what does that mean? That means that I have an X space, that I have one class that looks like this. Here's a normal with some variance. I have another X space that looks like this. So this is class 0. This is class 1. And what I just plotted for you is probability of X given that Y is equal to 0. This is probability of X given that Y is equal to 1. So I've drawn it in one dimension, but X could be 2 dimensions, 3 dimensions, whatever. You have some distribution described. So if it's a normal and the variances are the same, then your problem is fairly simple. So what I can do is that I can take the likelihood. So this is the likelihood, right? This is the likelihood for class 1. This is the likelihood for class 0. So suppose I multiply that by the prior probability. Suppose I multiplied by the prior probability. And why do I want to do that? Well, because the posterior probability of Y is equal to 0 given X is the likelihood, right, times the prior divided by the marginal. So that means that if I find a ratio of one class to the other, so say that I want to find the ratio P of X given Y is equal to 0 times the prior probability divided by P of X given Y is equal to 1 divided by prior probability, I'm finding the ratio of the posterior probabilities. Okay, let's look at that for just a second. So what did I just do? So what I wrote is that if I want to know the ratio of the probability of this input X being class 0 to the probability of it being class 1, what I need to do is to find the likelihood multiplied by the prior and divided by the other class. Because the marginal P of Y is the same in the two places, right? So it just cancels. P of Y is the same in the two conditions. So the ratio of the likelihoods times the priors is the ratio of the posterior probabilities. Yeah.
Shouldn't we divide by P of X equal X? Why do we divide by P of Y?
Oh, you're absolutely right. We're wrong. Yes. Yeah, thank you. The marginal is P of X. Yeah.
So in the last chart you drew, you had Y on the axis. And on this one, you have X on the axis.
Yes. Yes. So last chart I drew, we had projected our X into the output space Y. So it was a one-dimensional space. Here, I drew X as a one-dimensional, but X is in general is going to be a multidimensional space. So that's the input space now.
Yeah.
So in the input space, the likelihood, probability of X given Y is equal to 0 resides someplace. So for example, Let me draw it for you. So suppose this is X. Suppose X is a two-dimensional space. I have some white dots and I have some blue dots. So if I were to draw these as probability distributions, what I would get is I would get the following. I would get something like this, right? Some two-dimensional hump over here, and I would get another two-dimensional hump over here. So those are the likelihoods. So all I've done so far is multiplied my likelihood by the prior, and I've shown you how these guys look like. So what I'm suggesting to you is that the ratio of the posteriors is simply the ratio of the likelihoods times the priors. And if I find the log of this quantity, so if I find the log of the numerator to the denominator, this is going to be called log odds, and that describes something that's going to be easy for us to compute. So if I take the log of the numerator, and if this is a normal with mean mu zero and variance sigma, and this is some scalar quantity q, I want to find the log of this normal times this constant q. So that's just log of the normal plus log of q. So log of a normal distribution. So I'm just going to write this. This is going to be equal to, suppose x is some vector x1 to xm. So it's a dimension m. So I'm going to have minus log. There's going to be m over 2 log of 2 pi minus 1/2 x minus mu 0 transpose sigma inverse plus and then there's the minus 1/2 log of determinant of sigma plus log of q0. Right, so the normal distribution gives me these coefficients in front of the exponential. Here's the exponential where the exponent goes away because I'm finding a log, and here's the probability of y is equal to 0, right? This m is the size of x. So x is some vector of size m. And so this is a multidimensional Gaussian. So then you take 2 pi and you raise it to the power of minus m over 2. But thank you for asking. Okay, wonderful. So this is the log of one of these guys. So I can do the same thing. I can find the log of p of x given y is equal to 1 times probability of y is equal to 1. And why am I doing that? Look, because what I'm trying to do is I'm going to show you that this quantity here, if I take the log of it, is going to be something that's going to become quite simple. And so first I take the log of the numerator. I'm going to subtract from it the log of the denominator, right? That's how I do the log of a ratio, right? Log of a numerator divided by the denominator is log of the numerator minus the log of the denominator. So here's the log of the numerator. I have this quantity here. So if I now want to find the log of the denominator, it's going to look very much like this, right? Except that Q0 is going to become 1 minus Q0, and mu 0 is going to become mu 1. And everything else is going to cancel, right? Because I'm taking the numerator, subtracting from it the denominator, right? So this is going to look just like the above one. Okay, so now if I subtract, so if I now do log of the numerator, what I'm going to get is only the elements in the exponent. So this is going to have this subtraction here is going to give me some elements, and everything else is just going to be a constant that we don't care about. So this is going to become x transpose sigma minus 1 mu 1 minus x transpose sigma transpose mu 0 minus 1/2 and this quantity, if you look at it, look at the way x appears here. This is just W transpose X plus W0, because everything that X appears is linear in it, and then these are just constants. So what this is saying is that if you have two classes that have X's in which the variances are equal and they're Gaussian distributions, if the likelihoods are Gaussian, then log of P of X this ratio is going to be a line. That's going to cross 0 at the decision boundary. So your decision boundary is where the numerator is equal to the denominator. That's the probability of belonging to one class is the same as the other class. When the probabilities are the same, the numerator divided by denominator gives you 1. The log of that is 0. That's where this crosses 0. And going back to our two-dimensional example, what this is saying is that if you wanted to draw a decision boundary between these two classes, if these two classes come from normal distributions that have equal variance, then that decision boundary is a line between them. Okay? So that's if the variances are equal. The log of this ratio here can be written as a linear function of x.
In practice, do people like make that assumption that the covariance matrices are equal, or do they measure it?
Let's do it. Let's do it now for when they're not equal. Let's see what happens. Right. So if they're not equal, suppose now I have a situation like this. So I have one class that looks like this, and I have another class that looks like this. So this is now X, and I'm drawing for you the likelihoods times the priors. So this is probability of X given that Y is equal to 1 times its prior. And here's the probability of X given that Y is equal to 0 times its prior. Okay, so what this says is that over this region here, if I take the numerator divided by the denominator, it's more likely that I'm in class 0, but on the edges, I'm more likely to be in class 1, right? So that's clearly not a linearly separable thing, because in one edge, I am in class 1, in the other edge, I'm in class 1, in between, I'm in class 0. So in this case, what happens is that if I were to draw the log of this quantity, if I were to draw this here, now what I would get is something that looks like this. And that's a quadratic function. So now my decision boundary is not going to be a line, it's going to be a quadratic function. And this function here this is going to be not a linear function of x, but a quadratic function of x. It's going to look like this, which means that if the variances are not equal, then in the case of my problem, so if I have these two classes, now my decision boundary might look like this. So now I get a quadratic function. Okay, but in general, you know, how do I find things if it's not even a Gaussian? So maybe my distribution of my data is not even a Gaussian. So how do I proceed with that? Before I do that, let me see if you have any questions so far. So does this make sense what I'm plotting here? Does this make sense to you? Do you have any questions about that? So X is your input, and you know you're plotting your distribution. You just look at your data. You say, okay, these are the X's that belong to class 0. This is the X's that belong to class 1. Let's just plot the distribution. And there's going to be some overlap. So in this case, the overlap is so big that, you know, class 1 goes beyond the edge of class 0. And in this case, then the classifier has, if they're normal distributions, your classifier is going to have a quadratic decision boundary. But now the question that I want to think about is, what do I do if they're not even normal? So how do I proceed when my data doesn't fit a normal distribution? So what do I do in that case? Okay. Computing. This is what you're going to do for your homework, actually. Likelihoods when data does not come from a normal distribution. So what do I do now? So this is called, now what we're going to do is a procedure where I'm going to build a kernel. I'm going to use a kernel to form a new density estimation. So I'm going to use these little Gaussians. I'm going to put a little Gaussian on top of every one of my data, and then I'm going to sum up these Gaussians to form a distribution as the sum of these Gaussians. So if I have a whole lot of data in one region, then I'm going to have, you know, high density, and then at the outer parts, which may or may not be Gaussian, I'm going to have these little things. So I'm going to get a density that might look like this, you know, something like this, depending on where my data are. And I want to build such a function from the actual data that I have. This is called kernel density estimation. So the idea is put a Gaussian kernel at each data point. So let's begin with the simple case where X is a scalar. So what I want to do, I want to build P of X. That's what I want. I want to build a representation of my data, P of X. And let me show you how we're going to do it. So let's begin with X as a scalar. So I'm going to have a kernel, K, defined as a function of U, and that's going to be a Gaussian. So this has variance 1, mean 0, this particular kernel. So we have some data point, xi, my ith data point, and it's a scalar. And I have n data points. So now I'm going to build a probability distribution looks like this. So say I want to build P of X, given that, Y is equal to 1, let's say, class 1. What I'm going to do is I'm going to put a little kernel at each one of my data points and add them all up. So say X are all the data points that belong to class 1. So look what I did. I built a probability distribution made up of these little kernels that have the mean at my data point. And then there's this parameter H here. What's this H?
The size of the kernel, like the smoothing.
The smoothing. So, okay. What is H doing? He gave us the answer. What do you think? As I increase H, what's going to happen? Look at the distribution that I drew. Look at this here. Suppose that I end up fitting my data and I get this function. Let's say I increase H. What's going to happen to this function?
It's gonna become flat.
It's going to become smoother. Yeah, it's going to look like this. Wiggles are going to go away, right? Because I'm increasing the variance of my Gaussian that I'm putting on top of each data point. And so the smoother my Gaussians are, the wider they are, the sum of them is going to become smooth. Does that make sense? So it's a parameter you choose. How wiggly do you want your probability distribution? Yeah, does that make sense? Okay. So, all right, then this wasn't the case when X was a scalar. So suppose X is a vector, then what I'm going to have is K, my kernel, is going to be something that's going to depend on the size of X. So if X is an m-dimensional vector, it's going to be normalized as follows. Right? So this is my basic kernel. And what I'm going to do is build a probability distribution, a likelihood. It's going to be the sum of the kernels. All right, so let me summarize. So we can find for any class of, in my classifier, the likelihoods. You can find P of X given that Y is some class, because that's our data is labeled. So for each class, I can find the likelihood. Then what I do is that we can have priors. Probability of Y being that class. So we can find, next step is find log ratios. The log of the likelihood I can find the log ratio, which gives me the boundaries. So when this log ratio is equal to 0, when log ratio equals 0, you have the boundary. You have the decision boundary. Okay. So that tells you how you can use the likelihoods to find the boundary where you're going to belong to one class or the other. But we still haven't found the problem that we wanted. So my problem was, what's the probability of being in this class given X? So this is what I wanted. So all I've done so far is tell you how to find the ratios of the posterior probabilities. I haven't found what is the actual probability of belonging to this class, right? So that's the final step that I want to show you. How do I find that? Okay, so this is the posterior. That's what I'm really after. So let's go back to our ratio. So if I can compute this, if I want to compute this guy here, probability of belonging to this class with respect to the probability of belonging to some class K. So I can compute this ratio, right? Because the marginals doesn't matter, and the ratio up here, the log of this ratio here, this is this quantity. Okay, so suppose this is some value. Let's call it M1. So this ratio is something. I can compute this. So we can find M1. Because we have the likelihoods. All right. So let's work on this equation. So then this ratio is this quantity. So then this probability, this posterior probability of belonging to class I is this exponential times the posterior probability of belonging to class K. All right. So we know that the sum of the probabilities must be equal to 1. Right? So I have K classes. My posterior probabilities of belonging to class 1 through class K, if I add them all up, the sum has to be equal to 1. All right, so what I can do is write this sum in this way. I can take the sum of I is equal to 1 to K minus 1 plus the probability of Y is equal to class K given X. That sum is equal to 1. Let's replace the sum now with this equation. And factor out this probability of Y is equal to K given X. All right, so then this probability is this one, the sigmoid. So then probability of belonging to any class, J, so look what I did. I computed this guy here. I found a solution for this. So now if I want to know this probability, I just take the probability that I just found multiplied by the exponential of the ratio of the posterior. So this becomes divided by This is the posterior probability that I'm looking for. So if I can find the ratio of the likelihoods between belonging to class 1 to class 2 to class 3 to class 4 to class 5, if I have those log ratios, then I can use that to compute the posterior probability of belonging to any class, because that depends on those ratios here. So this is how we find not just the decision boundary, but the posterior probabilities of belonging to any class. Okay, so let's summarize. So what we did today is we said that we have some data that's labeled. We want to classify. We want to say it belongs to class 1, class 2, class 3. And in order to do that, we first used Fisher Discriminant Analysis. In Fisher Discriminant Analysis, you build a linear model that separates the classes based on a linear boundary. And in Fisher Discriminant Analysis, what you're doing is to take your data and project it onto some new space Y, where W transpose X is your output space Y. You make the means in the projected space of your two classes as far apart as possible, while the variances are made as small as possible. Okay, then what we did is that we showed that if you want to find the posterior probability of belonging to one class or the other, what you can do is assume a Gaussian distribution, or actually build a distribution, depending on, if you don't think it's a Gaussian, use kernels to build the actual distribution. But nevertheless, for any X, for any input that I give you, you can find the ratio of the likelihood. You can find this quantity, the probability of it belonging to one class versus the probability of belonging to any other class. That's just these guys. That's just these likelihoods that tell you how to find the posterior probabilities of belonging to one class or the other. So you can find this ratio. And if you can find that ratio, you can then find the posterior probability as a function of those ratios. Okay, so this gives you a way to classify data based on the statistical properties of the labels that you have. Yeah? Okay. If you have any questions, come up or raise your hands if anything didn't make sense right now.
Like intuitively, I can see how linear and quadratic systems can be done for like one or two classes. But when we extend to multi-class, my intuition makes me feel that there could be something wrong with still relying on linear models for multi-class and multi-classifications.
Right. So keep in mind that all we've done so far is to show that the ratios, these ratios are quadratic or linear. So those are just the boundaries. So that means boundary between, if you have 5 classes, that's okay. The boundary between class 1 and class 2 is some shape. The boundary between class 2 and 3. In fact, for your homework, you're going to do 3 classes. And those 3 classes are not going to be Gaussians. You're going to build a kernel for them, and then you're going to get this zigzaggy boundary between them. Yeah.
What's the initial projection of X into Y here?
The W transpose X. Yeah. So you have to find W, right? That's what Fisher Discriminant Analysis does. It finds a W that when you project it onto Y, you get the means of your classes as far as possible. And what we did in using these log of these guys was we showed that, well, if you believe that the two classes have unequal variances, but they're still normal distribution, then that boundary is going to have quadratic relationship. It won't be a linear function, but it still have a closed form representation. You can find the W. Now, next class, I'm going to show you how do we use the data to actually find these variables, and that's basically a trial by trial updating procedure to actually find W's when your your system isn't linear. Like, for example, here, how do I find these W's here? I didn't show you how to find that. I just showed you that they exist. Right?
Maybe you'll cover it in more than that, but with a quadratic boundary, how do you diagnose or how do you know that that structure is the real structure versus just like covariance estimation noise?
Yeah, so that's like asking, how do you know that the model is right, right? So if all you have is data, then the only way you can gain confidence about your analysis is to do bootstrapping. So you say, okay, I'm going to take a part of the data and I'm going to find my model that separates them. And then I'm going to do it again. That's how I gain confidence on whether I found, a good classifier. Like anything else, bootstrapping is a way to gain understanding of how noisy is your estimate. But Thursday, I'll show you how do you find these quantities here. But in terms of your approach for your homework, what you're going to do is indeed find these boundaries. You're going to find posterior probabilities when the data is not Gaussian using these kernel estimates. All right. Thank you, guys. Have a good Tuesday.